So students, we are in video lecture. So we are in video lecture 20, and I hope that, as I told you in video lecture 9, that you try out different combinations and derive it yourself logically, because there is nothing to mug up at all in the whole thing, and that you can logically put forward, okay, this is what I record, these are my inputs, this is what I do, and you can do it for case number 1, case 2, case 3, case 4. The important point that I would like to say here is, in the COH system, the fluids component, phase component, or the phase components in the fluids, you cannot, given the mineral nature of mineral assemblages that you have, that you get in the crust and the upper parts of the mantle, which are accessible from where you can sample rocks, which is not very deep. The assemblages, all assemblages, from all assemblages, you can't find everything. It's not possible. Why? Because some of the mineral assemblages that you have, you often can't find out everything that you want. The assemblages put some restrictions on what you can find and what you cannot find. Mostly, in this type of fluids, where you have CO2, H2O, O2, CO, CH4, and H2, yeah, these are the components. I will also write down pressure and temperature here. Yeah, these are the fluid components. And then you have activity of carbon in graphite. These are the intensive variables which you're looking at. Mostly, in 99% of the cases, the phase component that you can extract, the value of the phase, the value of the fluid component that you can extract from the mineral assemblages is limited. So normally what you have, you can find out is XCO2, XH2O, and XO2. These are the three mole fractions of fluid component that you can commonly find out. So we are limited in doing our things. Say, for example, you normally don't get XCO, carbon monoxide. And you can imagine that in the crust of the earth, which is the upper part of the crust, it's more oxygenated. And so the chance of getting carbon monoxide isn't very high. So you produce carbon monoxide in reducing conditions. Similarly, methane is not a very common fluid component that you get or there is evidence for. So this have to be all calculated in an indirect way. So the chances are that the maximum that you can get are these three intensive variables. And that too, what I'm saying is, this is almost the maximum. Normally you can find out 2 out of 3. 3 out of 3 would require very special assemblages. Very, very special assemblages can give you independently values of XCO2, XH2, and XCO2. Very difficult. Commonly, you get either of the two variables. Say, for example, in carbonate rocks, you normally can find out CO2 and H2O. Whereas in hydrous assemblages, you can find out H2O and O2. So normally you find out 2. 3 is you're very, 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 very lucky to get XCO2, XH2O, XO2 as independent variables. It's very difficult. Now let us look at, say, case number 2, where you have fluid present and graphite absent situation. graphite absent situation. And in this case, if you can see, your F value is C minus P plus 2, and that is 3 minus 1 plus 2, that's 4. At pressure, known pressure temperature, this translates to 2. Similarly, if you have case number 3, where you had fluid absent and graphite present, say in this case, graphite present, I will have F is equal to C minus P plus 2. Again it is 3 minus 1 plus 2. And again it's 4. And at conditions it's 3. It's 2. It's always like this. So both under these conditions, degree of freedom is 4. At known pressure temperature condition, which takes off or quantifies 2 variables, you need either of the 3. Either of the 3 would do. Chances of getting 3 out of 3 is almost impossible. And if you take 4, now you see it's fluid absent and graphite absent. So your F value now is C minus P plus 2, and this will be 3 minus 0 plus 2 is equal to 5. And at this pressure temperature condition, it should be 3. You're already asking too much from your mineral assemblage. It's not that it's an impossibility, but the chances of such assemblages, which give you independent estimates of this, is extremely rare. Normally you get it in metamorphosed marls. Metamorphosed marls that contain magnetite and hematite, or magnetite or hematite. Such cases, you get these assemblages. Otherwise, you're restricted to 2. Now, one thing I must say here, if you look at the independent reaction, phase component minus system component, you can see here that system component is always 3. You see, system component is always 3 because it's a 3-component system. And phase component, you can always see it's 7. So essentially, it is 7 minus 3 is equal to 4. So you have always 4 independent reactions. 4 independent reactions. You almost have no escape. This value does not change. In case number 1 it was 4, case number 2, case number 3, case number 4. It's always 4. Because the number of phase components don't change. These are the 6 fluid components plus 1 solid component. Whether it's quantified or not, if it's quantified, then it will affect the degree of variance. But it will not change the number of reactions. So you always have 4 reactions. When you have fluid present situation, like case 1 which I derived, and in this condition, you can have one additional equation, which is, as I told you, sigma xi equal to 1. The mole fractions of all that add up to 1. But if you look at case number 3 and case number 4, that equation is taken out from your hand. You don't have access to this equation. So, essentially, what I'm trying to say is, the number of independent reactions will always be 4. The degree of freedom would change. So here, for example, at a known pressure temperature condition, for fluid present, graphite present, and for this, it will be 2 plus 4, 6 variables. It will find out 6 variables. Why from this, you see, there are 2 variables here and 4 independent reactions. So you're inputting 2 values and you have 4 reactions. So total, you can find out 6 variables. How you can find out 6 variables? You see here the total number of variables is 7. You see, in all these cases, in these 2 cases, you see, the total number of variables are 7 here. Phase components are 7. Why is it that you have 2 plus 4, 6? Because here, you have sigma xi equal to 1, you get an equation. Do you understand? Sigma xi, so you get an additional equation other than 4. Have you understood? Other than 4. For this one, say for example, fluid present, you have two sets of input data, 4 independent reactions, so you can take into account 6, but you have 7 variables. 7 variables. But what you have is, these 6 variables that you have here, all are not independent. One is a dependent variable. So effect, because it's fully present. So what happens, out of this 6, for case 2, out of this 6 phase component, 5 components can be independently determined. One component is 1 minus the rest. So essentially 5 plus 6. That is why you have 2 plus 4, 6. In case number 2. In case number 3, it is fluid absent this time, so that equation that you are using is out of this. So now what you do here is graphite present. So the moment you have graphite present, your activity is equal to 1. So now you see 4 plus 2, 6. 2 input data plus 4 equations. You can find out this 4, 6 variables. Do you see that? There is no, don't mug up, just think logically and all will be fine. And all will be fine. So for case 3, you have 2 input variables, Gibbs phase rule, 4 independent reactions, 6 variables. Here you have 7. But active here, graphite is present. So this is equal to 1. So you have essentially 6 independent variables, 4 plus 2. 2 variables you are inputting, 4 equations remain, and out of the 6, 2 you are inputting, so 4 can be found out from 4 equations. So that is the important point. Here in case number 4, you see, you have the same 4 independent reactions, but now you have 3 input data. So out of the 7, because this is not equal to 1 now, in case 4, this is not equal to 1. It's not equal to 1 because it's graphite absent. And sigma xi is also not equal to 1. So what happens? You have 1, 2, 3, 4, 5, 6, 7 variables, and you have 4 independent reactions and 3 variables that you need to input. Have you understood? So essentially, you're finding out all the 7 variables. You're finding out all the 7 variables. It can be, I think what I will do is, I will do for case number 4 quickly because this is the easiest. Case number 4 is the easiest to solve. And then I will take up case number 3. Let me take case number 4. Let me take up case number 4. And let us say the input variables are The input variables are 1, 2, and 3. So the input variables are 1, 2, and 3. Okay? Case 4. Case 4 is fluid absent, graphite absent. So now, let's write the reactions. C plus O2 is equal to CO2. Let's say this is reaction A. From reaction A, what we can find? We know HCO2, we know XO2, isn't it? The 3 are the input variables. So if we know HCO2, if we know XO2, and we know HCO2, then we know C, activity of C. Why? Because it is HCO2 divided by Xc into XO2 is equal to exponential bracket minus 1 by RT into del G0. Right? So at this pressure temperature condition, this is constant. So if this is constant and you have input XCO2, you have input XCO2. So you can find out X graphite, so you can find out this. Now very simple. Now C plus O2 or half O2 is equal to CO. That's reaction B. So you have XCO divided by XC into XO2 to the power half is equal to exponential into, this is reaction A. So minus 1 by RT into delta G0 B. Right? Now you see, XO2 is your input data. XC, you have just found out. XC is, you have just found out. So you can find out XCO. As simple as that. You find out XCO. Now let's see what happens to C plus H2 is equal to CH4. Let's see. And we have still one variable, this one. So you have, let's say this is C and then D, H2 plus half O2 is equal to H2. Now, how do we find this? We know activity of we can't find it from C and D, we cannot find it individually. So we have to change things a little bit. Change things a little bit around. So how do we do it? Change things a little bit around. So we have these things. So, okay, and we know all these parameters. So we modify the reaction. We modify the equation. Instead of, I will keep it writing here so that you can see it. So let's see, we conceive of a reaction E. Okay, E. You will say, sir, there are 5 reactions, but I have not used CD. I have not used CD. So let's say CH4 plus O2 is equal to CO2 plus H2O. Right? CO2 plus H2O. So it's not still balanced because oxygen, hydrogen is 4, carbon is 1, but oxygen is 2. So this will be 3 by 2 O2. I will write it again. 3 by 2 O2. So you see, CH, I have not taken these two, right? I have not taken this two. CH4 plus 3 by 2 O2 is equal to CO2 plus H2. Now you see here. See, so I can write XH2O whole squared into XCO2 divided by XCH4 into XO2 3 by 2 is equal to exponential minus 1 by RT delta G0 E. Do you see that? Now here, you know XCO2, you know XO2, You know XH2O, so you can find XH4. Have you understood? So I have not taken these two reactions, I have taken this two reaction. So the reactions that I will use are A, B and E. If I have taken A, B and E, then I can find out XCH4. Have you understood? I can find out XCH4 because I know XCO2, XO2 and XH2O. All three are input variables. So I can find out XCH4, the only unknown. And now I am left with H2. Now you see, I will erase D. I will erase D and instead keep C. Now you see what happens here? XCH4 by XC into XH2 whole squared is equal to exponential minus 1 by RT into delta G0C. Now you see, CH4 we just determined, XC we have determined, and we are left with XH2, so we can find XH2. That is what I am trying to say. I had a reaction before which I have erased, but I have 4 equations, and all of them are independent reactions. Why I have changed it? So as to suit my input variables. My input variables to suit my input variables, or the variables that I have determined. To manipulate it, I take a reaction which was not listed before, I don't take that reaction, I create a new equation, and then I can derive CH4, and I have kept back reaction C. None of them, you will see, are internally derived. It cannot be derived by algebraic addition or subtraction. You cannot do it. Now that is the beauty of it. So sometimes you don't need to be straitjacket, but you also don't need to be too extravagant about things. You don't need to be too extravagant about things. You can just keep it simple. Always remember that I have my input variables and some variables I have determined. So I have to manipulate the reaction in such a way that I can use the values that have already remains to be calculated. Do you get my point? So that is what is important here. So this is for case number 4, where there is no fluid, no graphite, and yet you can find out all parameters, all the variables. Here you had 3, and using these 3, you determined 1, 2, 3, 4 more. Using the 3 input variables and the pressure temperature of quartz, you determine 1, 2, 3 and 4 variables. So that is the important part of it. Have you understood? That is what my advice to you will be. Always keep your logic straight. Always keep in your mind that you're thinking logically. As I said, you don't need to overwork and make things as complicated like, I've written such a big equation. You don't have to. At the same time, you don't need to be extravagant also. You don't have to do it. You don't have to think too much about it. It's all there. You have to see it simply. That is why I've always used mole fraction here and never the activity terms. If I like the activity terms, you will not be able to find, because among the equations you will be completely lost. That is why I've kept the mole fraction. Think simply. Think very logically, and all will be yours. Right, so this is the expression. Now, for example, since we have done this case number 4 now, let us do another one which is anything, I don't mind. I will do one more for you so that you understand it. So let's say we take what? Let's take reaction 3. Case 3. What was case 3? I don't remember. What was case 3? Case 3 was fluid absent, graphite. This one's just getting out of control. Fluid absent, graphite present. Fluid absent, graphite present. And we know the F value for this is equal to C minus P plus 2, 3 minus 1 plus 2, that is 4. At known pressure temperature we have 2. So you have the option of either this or this or this. Any two. Any two will do. We don't need 3. Any two will do. So let's say, just for the sake of it, let's say we take XCO2 and XO2. XCO2, let's say we take XCO2 and XO2. Fluid absent, graphite present. This is, you will see we will land up in trouble. You will see we will land up in trouble. So the first reaction is C plus O2 is equal to CO2. That's equation 1. So now you see here, in this expression, graphite present, isn't it? So this value is equal to 1. We know this, this, and this. This is bad. This is bad. Because, you know, if in that equation that you have written, graphite present, so it's known, O2 you have determined as an input, CO2 is a dependent which is input. So this equation is a completely bogus equation to use for this set of variables. Let's try. I also don't know where it will go. So let's try. Then we have C. You see, we have not used this expression. We just wrote this expression. We have not used it because all 3 parameters are known. Now, C plus O2 half is equal to CO. This is B. Now, in this, for example, we can write XCO divided by XC into X into XO2 to the power half is equal to exponential minus 1 by RT into delta G0B. Now here you see, you know XC and you know XO2, so you can find out XCO. Here you know this parameter. Yes, also here I will erase it. These 3 parameters are determined. Oh, we were not talking of H2. Okay. So we have taken these 2 parameters here. CO2, activity graphite is known, and XO2. These are the 3 variables that we have. Now, from these 2 variables, we have been able to find out XCO. Okay? We have only taken till now 1 equation. We have only taken 1 equation. So now the problem is we have to find something else, and we might land up into not being able to solve the equation. But here you have fluid absence, so you don't have that sigma xr equal to 1 in your pocket. You don't have it. So whatever you have to do here. So you have to, let's think of modeling the reactions. As I said, this is already a bad expression because all three variables are known and we have taken all three variables. So actually using the variables we did not get an output, and that is a big problem. You did not get an output from it. So let's see if we can proceed further. We only got XCO now. We had XCO2, CO and activity graphite. We got XCO. Now we come into a more complicated part. Difficult to do. I'm just trying to write. Okay. Maybe there is hope. Maybe there is hope. Let us wait. So 2H2. So hydrogen is balanced, graphite is balanced. This is an equation. Let's say this equation is C. But it's not helping. It's not helping the case because both are unknown. Both of them are unknown. We know C plus O2. No, I don't think you can do it. So with XCO2 and CO, you have wasted a whole equation. So that is a problem here. That is a problem. We only could find out CO. Here also it's also a problem. I don't think we can be able to find that out. I don't think we will be able. So although we have found out two variables, I don't know. I don't think you can find out the variables because of technical reason. One is the technical reason is that in one of the equations, all the three are known. Let's see what happens. Okay, let's see. You can try yourself and find out. If you find out, you can write to me to the Google Classroom. I don't think it's solvable, but you can write to me if you find a solution. So that is why I think you should just try and see what happens. Yeah. Let's say if instead of CO2, what would have happened if we took XH2O and XO2? What would have happened? Let's say if we had taken this, then what would have happened? So, in this case, C plus O2 is equal to CO2. Okay, so activity, you see graphite present. So this is reaction 1. So the input data that we have here is XH2O and XO2. These are the input data, and you know the value of graphite, right? So from this one now, from this one we can write XCO2 divided by XC into XO2 is equal to exponential minus 1 by RT into delta G0A, and this I think you can find out because you know X graphite, you know XO2, and so you can get the value of XCO2. So you can get the value of XCO2. We are doing better now. So now, for example, C plus half O2 is equal to CO2. Let this reaction be B. And so now you have XCO2. No, this is CO. So XCO divided by XC into XO2 to the power half is equal to exponential minus 1 by RT into delta G0B. Now here you see XC is known, XO2 is known, XCO is known. Now I can get out XCO value. So here we get XCO values. Now let's see what we can do. Here. So now, okay. So now H2 plus half O2 is equal to H2O. Right? So now you can see this is reaction C, and you have XH2O divided by XH2 into XO2 to the power half is equal to exponential into minus 1 by RT into delta G0C. Now you see this is a constant, and you have input data of XH2O and you have input data of XO2, so you can find out XH2. So you can find out XH2, and then you have C plus H2, 2H2 is equal to CH4, and this is D, and then you can write XCH4 divided by XC into XH2O, XH2 whole squared is equal to exponential minus 1 by RT into del G0D. Right? And so, you know XC, you know XH2, so XCH4 can be determined, and so you have found out everything else. So, by input data of H2 and O2, with equilibrium with the graphite, you could find out 1, 2, 3, 4. 4 more data. And this is a fluid absent situation. So all these mole fractions are independent of each other. So that is what I am trying to tell you always. That you see sometimes what happens, like the last time we got stuck, and I will still ask you to find out if there is an answer. If we take CO2 and O2, then you have a reaction C plus O2 is equal to CO2. So all the variables in a graphite present situation. So your XC is known, XCO2 is known, XO2 is known. So what happens? You have everything known, you have overdone the reaction, which it's impossible now to find out the other variables. But you can see, if you can find out XH2 and O2 with a graphite present assemblage, then you can work it out. So there are ways to get out, ways to manipulate the system a bit, keeping the structure same, manipulate the reaction to extract things. But sometimes, for some assemblages, it may not just be possible because of some technical reason like that what we saw before. Yeah? So I think I have come to the end of this part of the session, which we started in January, essentially which is basically computing numerical analysis of thermodynamic reaction to extract metamorphic variables. this part, I think we have come to a conclusion. Next class, we will start on what is called progressive metamorphism of siliceous dolomite or dolomitic limestone. We will dolomitic quartzite. We will do that, and that's very interesting because it gives you an insight as to how metamorphic reactions work, one after the other, as a function of temperature. We will do that. But I think I will write in the classroom. So this is how things are, and sometimes you might just get caught up into some sort of situations like XCO2 and O2 situation, where the equation is there, but all the values are quantified. So the rest of them cannot be determined. Because after all the 4 reactions, you put in something and get something. But if you have a reaction where you put in everything which is already there, well, the equation is lost. And that's a major problem. Okay, I think you have done enough exercise. I have shown you case 1, case 3, case 4. I have not shown you case 2. It's case 2, remember, fluid present situation. So fluid present situation, sigma xi is equal to 1 is always there. So that's a big headache solved. So use that equation as much as possible and put it in such frame that you have a quadratic or an equation so that you can solve for one of the fluid phase components. Okay, I think I stop here. We will continue on metamorphism from video lecture 21. Thank you. And some of these days I have forgotten which day we wanted to have the examination. We will have the examination soon. Right? I think I already gave you the day. I will check it up again. Right. Thank you.